Okay, let's see how to use a parametric approach in practice. We will consider uniform distribution, which is the simplest distribution you can think of, where all events have equal chance to occur. For example, when you roll a coin, and if coin is unbiased, it's kind of a uniform distribution because both tails and head have equal chance to occur. If you roll a die, it's also uniform distribution because every outcome of rolling a die have equal chance to occur, right? So, of course, it's not a good examples for uniform distribution because uniform distribution assumes that number of events is infinite, while in rolling a die and, for example, tossing a coin, you have infinite number of events. But let me show you another example. Let's say we have a fortune wheel. Let's say that number of these outcomes, so these ones, is very, very large. Okay, so you can have, for example, here you win $100, here you win $101, $102, and so on and so forth. So you have a lot of these particular outcomes, right? So every time you roll this, you win a particular amount of money. Okay. So what you see on these plots, it's a fortune wheel results with 100 trials. So I roll this wheel 100 times, and then you can see all possible outcomes. So this is density distribution, empirical density distribution, and this is the percentage values. Let's try to fit this empirical data with theoretical distribution. Well, theoretical uniform distribution has two parameters only. It's the smallest value and the largest value. So if you know the smallest and the largest value, in my case, it's $100 and $1,000. So this is the smallest win, and this is the largest win, the largest outcome. Then the density distribution function looks like this. If your value is outside, then it's 0. If your value is inside, then the density is simply 1 divided to max minus mean. And the plot, you can see it here, it's simply a rectangle. You remember that for density distribution, the area should be equal to 1. So this is why. So this is mean, this is mean, this is max. So it means that the length of this is max minus mean, right? So therefore, the density, in order to get area equal to 1, this density should be 1 divided to max minus mean, right? And the density should be the same because the chances to get any outcome is the same. So the density for all these events, for all these outcomes is the same, okay? So this is the probability density function. And then you can see it actually fits our data very well. Of course, we have empirical values which are a little bit larger or a little bit smaller than the expected probability, the expected density, sorry. But that's okay because it's empirical data, it's experimental data. You always have experimental data deviates a little bit from the theory, right? Now we can also define the cumulative distribution function, this one. Yeah? You can see that in this case, you take x, subtract the smallest value, and then you divide to the range, the max minus mean. So the expected theoretical cumulative distribution function, the probability cumulative distribution function is just a line. And you can see that this line fits our points very well. So our points are very close to this line, right? So the empirical points. Okay. Now let's learn how to use these functions. Well, first of all, the CDF is the most important function because CDF let you compute probability for a given value. Let's see how we can use the CDF function. Well, let's compute a chance to win anything below $800. So x is equal to 800. So strictly speaking, we would like to see what's the percentile, what's the percentage values for the 800, right? You remember that usually how we do that, we simply count how many outcomes in our empirical data is below 800, and that gives us the percentage. But now let's calculate theoretical value. How we do that? Well, we simply need to find, for given x, this is the given x, we need to find a corresponding 0.8, which lies on this theoretical line, right? So we know the equation of the line, we know x, we know mean, we know max, we know everything we need. So we simply do the calculation. So the probability to get a value below 800, it's 800, this is our x, minus smallest value, 100, and then divide to the range, the difference between max and mean. That gives you a probability of 0.78. So it means that in 78% of the outcomes, you will get a win 800 or below, right? Now we can also, for example, compute a chance to win 400 or below. The same idea, we just use the theoretical function for that. So 400 minus 100 divided to the range, that gives you 0.33. Yeah? So remember that the chance to get a win below $800 is 0.78. The chance to get a win below $400 is 0.33, right? But what it means? It means that we can compute a chance to get anything in between. It's simply a difference of these two values. So the chance to get any outcome between $400 and $800 is simply a difference between these two outcomes. So it's a difference between 0.78 and 0.33, and that gives you 0.45. So the chance that you will win anything between $400 and $800 is 0.45. So in this case, you can see I didn't use the empirical values. I didn't even show you the empirical values, the values that I got, all these gray points. I simply used the theoretical function and parameters of this theoretical function that I derived from the empirical values. So I derived two parameters, min and max, and then I use theoretical function because it fits my empirical data very well. That's exactly what parametric approach is. Use your data, use your sample values to estimate parameters of theoretical distribution function. If you see that the fit is good, so the theoretical distribution function describes your empirical values well, then you simply use these parameters to do all the calculations. For example, you can use CDF function to calculate different probabilities like I showed you right now. What else you can do? Well, you know that CDF function, the cumulative distribution function, gives you probability if you know a value, right? So if you know a value, you can always compute a probability. But sometimes you need to do the other way around. For a given probability, you can compute a value. And that's what you can do with inverse CDF function. So if you take this and swap x and y, so you can see now p is here, the probability is here, and the value is here, right? You simply swap x and y. That's exactly a CDF function. For uniform distribution, CDF function looks like this. So this is a probability of interest, and these are parameters. These are parameters, right? Let me show you how to use it. Let's say we would like to compute first and third quartile for this distribution. How to do that? Well, we know that first quartile corresponds to probability of 0.25, right? So we simply put 0.25 here, and we know already max and mean, it's 100 and 1000, so we can compute it. So mean plus the probability of interest times range, that gives you the value. So the $325, this is the first quartile. What it means? It means that in the 25% of the smallest wins will be up to $325, right? Then you can compute the third quartile. We know that for the third quartile, the probability is 0.75. So we know that third quartile, it's a boundary between 75% of smallest values and 25% of largest values. So we simply put the probability here and compute that it gives you 0.75. So it means that the 50% of most common outcomes, it's exactly the IQR, right? So it's what lies between Q1 and Q3. It's between $325 and $775. Again, you can see that I don't use the empirical data here. I used empirical data only once to find these two parameters. And then I simply use, in this case, probabilities to compute the values. So now I can compute different intervals based on inverse CDF function. Well, for uniform distribution, these functions are very simple, but for other distributions that we are going to learn, they can be a little bit more complicated. So therefore, we will use R to do all the computations. So R has CDF, PDF, and ICDF function for almost any distribution implemented. For example, for uniform distribution, you can see that CDF function is called P-unif. Unif, it's a name of distribution. Uniform P means it returns probability, right? Inverse CDF function, in this case, it will be Q-unif. Again, unif, it's a short for uniform, and Q, it's a quantile function because in fact it gives you quantile, right? For the given percentage, it gives you the value, right? And then you can, for example, do the computations by simply put all these values. So this is $800, the smallest value, the largest value, the mean, and the max. And that gives you the probability. And that's exactly what we have calculated manually, right? And then similarly here, you put the probability, you put the mean, you put the max, and that gives you the value. It's exactly what we also found together using the manual calculations. Okay.